Today we're going to go over a little bit about data preparation. And this is going to be some introductory R, and it's also going to involve a little bit of discussion about things that are specific to nested data. So the first thing we want to do when we're starting a new session in R is clear our working environment. We can use this with this rm list equals ls function that just makes sure that there's nothing floating around in your R environment that you don't want in there. It's a good habit to get into doing this whenever you start a new project. Then we want to set our working directory, just so we know how to access local files on our computer. We do this with the setwd function. Then we put the directory in quotes, and just remember to use forward slashes, not backslashes. Backslashes have a special function in R, so we can't use them here. Next, we want to read in our data, and we're going to look at this pane data, which is data that we're going to use a lot throughout the semester here. So you may want to follow along with what we're doing, because we're going to modify it a little bit just to make it a little bit easier to access later. So it's currently in a .txt file, so you can read it in with the read table function, and I'm just assigning it to the name DAT. So DAT is what it's going to look like in R. And one of the issues with this data set is it doesn't come pre-built with the column names, so we have to specify them manually. And a lot of times you'll find data like this, especially in text or .dat files. So we can specify the column names or the variable names of our data with the call names function, and then we're going to assign them using the C function, which is short for concatenate. And the C function essentially just creates a manual variable. So here we're just going to specify each column name individually in quotes with commas in between them, and then we're assigning those to the column names of DAT, and then the column names will be in there. And then one thing you can do now to make your life easier later in the semester is you can now save this new data with the column names in there to a CSV file. You can use the write.csv function to save the new data with the column names to pane.csv. And remember to specify row names equals false because our data doesn't have row names. If you don't do this, you'll just get an extra column with one number for each observation, so it'll go from 1 to however many observations are in the data set, in this case 2003. And then we can read the CSV in with the read.csv function. And as you can see, when we do that, the column names are now in place, and we don't have to worry about specifying them manually anymore. We can also read and write data for other software. The only thing with this is that you don't have built-in functions in R to do this, so we have to use a package. In this case, I'm using the Haven package. One of the great things about R is that lots of people are adding on to it by building packages like this. I'm not going to go into too much detail about this. This is just helpful to know if you want to transfer data between R and SAS or SPSS. I'm just going to go over how to install the package. So first, whenever you're adding a new package to your environment, you have to use the install packages function with the name of the package in quotes. You only have to do this once the package is installed. You do have to load it every time you start a new session and you want to use it, and you load it with the library function. And then you can write data to SAS or SPSS files, or you can read them from SAS or SPSS files. The Rio package also has a nifty little generic import function, which doesn't really care what file type it is. It'll figure it out for itself. So you can import using .sav, .csv, .sas files, whatever you want. So it's good to know about that too. We'll often use this Rio package because it's so generic and flexible. So to get a little bit of a snapshot of our data, we can use some of these different functions here on this list. This data is a daily diary study about pain and affect, and we're going to go over how to look at our data and summarize it in a couple different ways. First, we can check the number of rows in our data. Again, this is 2003. We use the nrow function for that. We could check the number of columns or variables, which is ncol. So in this case, we have 24 columns or variables. And we can look at the names of the columns using the call names function, as we talked about before. The head function is useful for getting a snapshot of what your data actually looks like. It'll give you the first 6 rows of each column of your data. So here we see every column of our data, but just the first 6 rows, and we see each of the first 6 rows has the same person ID, meaning each of these observations comes from the same person, but it has a different day ID. You see, so the day ID varies from 0, 1, 3, 5, 8, 9. That means that these are different daily observations from the same person, and this is the type of data we're going to be dealing with in HLM. If we want to look at fewer or more rows, we can use the n argument in the head function. Here I set it to 4, so now we're only looking at 4 rows. And the structure function, or str, is another way of getting a snapshot of your data. It shows you all of the column names, and it tells you what type of variable each column is, and it gives you a little bit of what the first few observations look like. Finally, there's the summary function. If you call summary on a full data set, it'll give you this sort of numerical summary where it gives you the mean and median, minimum and maximum of each value. It'll do something a little bit different for non-numeric data, but it's useful to know about this too. Finally, the $sign operator is the way we access individual variables in R. So in this case, we're looking at the p-affect, or positive affect variable. So if we call dat $sign positive affect, that means that we just want to look at that column. So we can call the mean of that column or the standard deviation of that column. And if we just call that column, if we just call dat $sign p-affect without any function, it'll just print out the full column. Now we're going to talk a little bit about data formats and data structures, which is an important concept in nested data. So in HLM, remember, we have 2 levels of data. We have clusters, and then we have multiple observations for cluster. In this case, we have the level 2 variable is persons, and then we have multiple observations, which are daily responses, and that's our level 1. So this data is currently in the long format, which means that we have an ID column for participants, and then we have multiple rows per person. And this is how we're going to want things in HLM for the most part. We want things to be in this long format with multiple rows per cluster. But sometimes you're going to see data in a wide format where you have 1 row per person and then several columns for repeated observations. And that's not how we want things in HLM for the most part, but you will sometimes get data that comes in that format. And it's good to know how to pivot from one direction to the other. And the easiest way to do this, I've found, is with some functions in the tidyr package. And we're going to take an example where we have data in the wide format. This dailyaffect.csv file is daily positive affect readings for different people in a wide format. So here, if we call head on this data set, we see that there's 1 row per person, and then each column represents a different daily positive affect reading for these people. And so this is in the wide format, and we want to get it into the long format. And to do that, we're going to use a function called pivot longer. And the arguments for pivot longer are, the first argument is the data set that you want to pivot. The second is the columns that you want to take and pivot from wide to long. So remember, the first column in this data set is the ID column, so we don't want to pivot that one. That's our ID column. We want to pivot everything from the second column to the last column. So we call from 2 to the last column, which you can always call the last column of a data set by calling ncol in the data set, because remember, that tells you how many total columns there are. So this is saying 2 to the last column by saying 2 to ncol of the data set. Then the next argument is the names2 argument, and this is identifying what you want to name the new column of the day identifiers. So remember, the day IDs right now are the column names of the wide data set. So the names2 is saying, this is what I want to, what the name of the column that represents the column names of the wide data. So that's what we want to do there. And then for the data we actually want to pivot, we use the values2 argument. So this is the final column, which is the actual positive affect readings, and we have to tell it what we want to name this column. So it's going to be positive affect. And now take a look at what happens if we run this function. We see now, instead of wide data, we have long data where we have multiple observations per person, but we have 3 columns, one with the day identifier. So this is the multiple observations for person 1. You see data 0, 1, 3, and then the last column is the positive affect column. And if we go back and look at person 1, we see the first row matches is going to match what's in the long data set. So 6, 6.75, 5.75 are the first 3 observations there, and here they're the first 3 observations in the p-affect column now. We can also pivot wider. We're not going to need to do this as much in HLM. This is more for other data techniques. For example, SEM likes data in wide format, so you may want to take a look at this, but I'm not going to do more than reference it here. And this is what happens if you convert your long data to wide data. You get it back in the original form.